Hello, everyone, and welcome to the next part of our CP Bootcamp based on CSCS series, whatever it is. So, uh, I know I haven't been making any videos recently, but that is because I've moved to Japan and I'm living alone right now. So, I have to deal with a lot more stuff than I had to before. So, it's a lot of pain, but finally, I've sorted a lot of stuff out and making a lot more time for myself. So, now back to making videos, I guess. So till now we have covered introduction, time complexity, sorting, and data structures, which I call the phase one of this series because just using those you can actually go quite far in competitive programming. So I hope you have been practicing and not just complaining about new videos. But if you have been practicing, which would be good, uh, now we can move on to the next part, that is some more advanced algorithms and data structures, which will help you to do more tougher problems. So, for today, we're going to be covering complete search. So, what complete search is basically, so essentially, many times, what you have to do in a question, in a problem, is you have a lot of elements. You have to pick some of them, right? So, essentially, the optimal solution is using some of these elements, right? So it combines them through some operation, right? And gives the answer. And this is essentially what we have to do, right? Many times. So to do that, we try to optimize and stuff, but there is obviously a universal way, which is more commonly known as brute forcing, right? So complete search essentially searches every possible solution and that is brute forces on every possible solution and figures out what is the best solution. So for example, let's take a problem where we have an array, right? So clear, let's say we have an array of elements, and what we have to do is tell what is the sum, what is the minimum sum we can get by adding five distinct elements in this array. Well, obviously, the answer would be to sort it and then add the first five elements. But what if we are not allowed to sort, right? So, what is the way to do it via brute force? The way to do it via brute force is to just check all the subsets of size 5, right? And then calculate their sum and then take whichever one is the minimum, right? So, that is essentially how you can use it. Now, this was a very weird example because you have a very simple solution, but um, there can be other questions where you don't have a direct solution. So for that you can try brute forcing. So let's see, now to do this brute force, right, we have to generate these subsets. So how to generate these subsets, that is what we're going to be learning. So first of all, what are subsets? You can read this, right? So subsets of 0 1 2 are null set, right? So 5 0 1 2 0 1 0 2 1 2. So essentially all the possible grouping of elements, right? And how many are such subsets? There's 2 to the power n, if n is the number of elements. Why? Well, it is very simple. I think you must have done it in other what, actually I want to use Excalibur. Yes, yeah. So uh where was I? Right. So let's say you have n elements, right? Now, to create a subset of these elements, what you can do, you can either pick this element or not pick this. So there are two ways. You can pick this or not pick this, so two more. Pick this, not pick this, two more, and so on. And this is happening how many times? N times. That is 2 to the power n. So there are 2 to the power n subsets, and how to generate them so that we can operate on them. So first way that they have mentioned is recursion. So we can find out all these subsets by going through every possibility through recursion. Now, how is that working exactly? So let's have a look at not this, but yeah, back here. Actually, I'm gonna move this here because I have a habit. Yeah, so this should be good. Okay, so how can we generate the subset? Just the way we try to count it. We can first try to choose this and then try to not choose this, right? So let's say these elements were 1, 2, 3, 4, and so on. So we can try to choose the one or not choose one. Okay, so empty. Then we can try to choose two or not choose two, right? So empty. Here we try to choose two or not choose two. So as you can see, this will keep on increasing, and since the computation, the essence of the computation we are doing is choosing or not choosing the current element that is being repeated, we can try to do it by recursion. So let's try to code that recursion, and it will all be clear once we get into it. So I think I use this now. Okay. So yeah, this is the code from before. We can just get rid of this. So let's say the elements are from 1 to n. Okay, and let's keep n a little bit smaller. Now how do we choose these elements? So let's make a recursive function that makes our subsets, right? Subsets. And let's try to see what we have to do. So the computation that I told you was choosing or not choosing the current element. So we want the current element, right? So now we can choose it or not choose it. So one time we will choose it, right? So let's have a, first of all, we're going to need some storage to store the current subset, right? So I'm just gonna have a vector global because why not? So one time we're gonna choose it, right? And then we recurse, right? That's how you do recursion. And essentially we move on to the next element. And then the other time we don't choose it, right? So let's remove that element and then do that. So, right. Easier would be to just call the next recursion method before and then push it, then call it again, right? So don't choose and choose. Okay, so this is our recursion, but we also need a base condition. What is the base condition? When does recursion eliminate? So when does recursion eliminate? When we are out of elements. So if current is equals to n, right? Let's actually move this here as well. God, I have removed vim controls. It's giving me some issue. So once we do that, we can just print the elements, right? Like this, and exit. Okay. So I hope that makes sense. That is why I always, first of all, try to write the crux of the recursion and then the base condition. Whenever you are in doubt, just ask yourself, like, what is the main functionality of the recursion and what is the base condition? When does it eliminate? And you will find out the answer. So let's call this function, right? And we're gonna start with one, right? So let's call this. Okay, where is cph? Here it is. Run all. And as you can see, we have all the subsets. So 2, 4, 6, 8, 10, 12, 14, 15. And there's actually another, which is nothing, right? So that, where is that though? Anyhow, this is our method to get all the subsets, and essentially here what we have to do is do the processing, right? So if we want to, let's say, minimize some quantity, we calculate that quantity here, right? So calculate the required quantity and then store the optimal one, right? If you have to take the minimum, take the minimum. If you want to take the maximum, take the maximum. So that's how we do subsets. Now, and as you can see, this is the search tree. And if you have watched my previous videos, you should know that the size of this tree is n. I mean the height. Why is it n? Because the number of elements here is 2 to the power n. And when you log that, when you do log 2 to the power n, you get n. That's how you get height of a binary tree, right? So yeah, that was that. Okay, can I get rid of this? So what will be the time complexity? Well, time complexity would be uh, how many elements are there? So it should be 2 to the power n, right? Okay, so now this was recursion and this was obviously extremely slow, right? Because so this algorithm in itself is very slow because we have all these subsets, right? And getting all those subsets is going to take a lot of time because there are a lot of subsets. So this algorithm is just in general is slower, but it is made even more slower with all those recursive calls because recursion is slow. Why is recursion slow? Because there are a lot of function calls. Why are function calls slow? Because you have to do push and pop on the stack to do the call, right? I'll, I mean, essentially what happens is you store all the current registers onto the stack, then you jump to the function location, and then you execute that function, and then you uh, jump back to where you were, and then you pop back all the things you pushed onto the stack. So it's a heavy thing. Anyhow, that was one thing. So can we try to make it into an iterative process? Well, to make it into an iterative process, that is the method 2 they have described here. Here's an interesting thing. Let's look at binary numbers, okay? The binary representation of numbers. So what is this? This is 2, 4, 8, 9, right? So this is 9. And actually, forget this. Let's just take this. This is what? This is 7, right? 4, 5, 6, 7. Now, let's take all the numbers from 0 to 7, right? So 0 is 0, 1 is 1, 2, 3, 4, sorry, 4, 5, 6, 7. Okay, and if you pad all these numbers to 3 digits, you'll notice that they represent subsets, right? If you were to take an array of elements of 3 elements, right, and 0 represents not taking that element and 1 represents taking that element, then notice how many elements these are. They are 2 to the power 3, right? And 2, 4, 6, 8, right? So there are 8 elements and every one of them is unique. So every one of them will correspond to a subset, right? So what we can do is use this binary representation as a mask as to what is in our current subset. So if we iterate from 0 up to this number, right, which is the binary representation, right? So if we want 3, right, so for 3 what we want is a number that has one in all of its positions, right? All 3 positions. So what is that number? That number is actually less than 1 less than this number, right? If you add 1 to it, it is less than, if you add 1 to this, right, you get this number. And this number is actually what you get if you bit shift 1 3 times. Okay. So yeah, that is just a basic observation. So what you can do is iterate from 0 to 1 n, right? You don't include this number, but up to this number. Okay, so you go to all these numbers, and now every number, if you represent it in a bitwise in a bit representation, right, you get a mask for a subset. So that's exactly what they have done here. They iterate from 0. So b, okay, this is kind of trash. Let me code my version. So let's have vector again. Okay, now subset mask. Okay, so subset mask starts from 0, and we iterate till it is less than 1, less than a dot size, right? And subset mask plus plus. Okay, and notice that you can only do this for like 32 or 64 length, up till 32 or 64 length arrays, because this will overflow otherwise. And let's say if a dot size was greater than 31, then you will have to use long. Okay, so we get the subset mask, and then also you will have to use long here. So anyhow, we get the subset mask, and now what we have to do is try to use its bit representation to get the element. Okay, so let's make our subset, right? Now let's iterate. Okay, let's store n actually. Now here I can just use n, and here as well, right? Now if you want to use that element, right, if you want to use the ith element, is decided by what is the bit value of subset mask at I, right? So let's say the subset mask is 1001. Okay, so in that case we want to take the 0th element and the 4th element, actually 0th element and the 4th element, right? Because uh, this is the lowest bit, this is the 0th bit, first bit, second bit, third bit, right? So to get the 0th element of A, or to get the ith element of A, what we want is ith bit of mask to be 1. How can we check if the a bit of a mask is of a number is 1 or 0, right? So uh okay, I might have not explained this bit shifting operator, but what it does is, so let's say you have a number 1001, shifting it to the right one time, right? What it does is it shifts it to the right one times. So 100, this last bit gets removed, right? Because it is shifting to the right and there's nothing more to the right. So we get 100, and think of it like there are more zeros, so zeros, right? And if you were to shift this number to the left one time, what will happen is this one bit will get discarded and you'll get 0, 0, 1, 0, 0, 1, 0. And okay, so notice that everything goes to a higher or a lower bit in these operations. That is, there is an integer division or multiplication. If you move to the right, that is, you're making every bit divide by 2. What you're doing is dividing by 2. And it is integer division because if the last bit was 1, it is getting discarded. And if you move to the left, right, if you do that, what's happening is every bit is getting multiplied by 2, right? So yeah, that's what bit shifting is. Pretty simple if you know what is happening. So how to check if a bit is uh, you know if an ith bit is 1 or 0? So what you can do is, okay, back to the example 1001. I want to check if the third bit, right, 0 1 2 3, third bit is 1. To do that, what we can do is shift all the bits. Okay, what we can do is shift it 3 times. So 1 time, 2 time, 3 time. So what this will ensure is that the ith bit that we want to check is at the lowest position, and then what we can do is take an AND. So it is, maybe let's say it was like this, right? So this was the representation, right? Now so these three got discarded, and we have this. Now we are sure that the ith bit as the, okay, why am I messing up? Okay, so the ith bit is at the 0th position. Now we can take a bitwise AND with 1 to know if it is 1 or 0, because if it is 0, bitwise AND will be 0, but if it is 1, bitwise AND will be 1. So what we have to do is check if AI right shift I times, right, and 1, if this value is equals to 1, right, obviously we can just remove the equals 1 position. Then we push back to our subset AI, and then let's just print our subset, right? So actually, let me, okay, what was that? Subset for mask, subset for mask. I haven't coded in a long time. I'm kind of bad right now at coding. So for auto X in subset, right, what we have to do is let's just print X and then print a new line. Okay, I'm bad. So yeah, now we can print all the subsets. As you can see, subset for mask 0 is okay. Okay, there's something wrong with this. Yeah, whoa, not AI, subset mask, right? So yeah, subset for mask 0, nothing. For 1, we take the first element. For 2, we take the second. 3, we take the first 2 elements, and so on. And obviously here you just do the processing, right? Process your elements and find the quantity. So yeah, that was how to calculate subsets using an iterative method. Obviously there is a limitation that we can only do it until our integer does not overflow. So that's like 63 elements. So yeah, that was method 2. Alright, so besides generating subsets, we also may need to generate all the permutations in some problems to brute force all the possible ways. So to do that, we can again use recursion, and that is what we're going to be discussing. Now obviously, usually you don't need to generate all the permutations or all the subsets because they are a lot, and usually you have some other option, but there are many questions where you have to do it. So yeah, let's see permutations. So let's say you want to generate a permutation of this. Now if you're thinking, why do I already have written everything here, that is because my recording went corrupt for this section of the video. So let's say you want to permutate all these. So permutation is essentially rearrangement, right? So what you cannot do is what we did previously, right? You take one or you don't take one, right? Because the next time we still have one in option, right? So if you do that, what you will get is an infinite loop, right? And also this, there will be a lot of repetition, so this is just not correct, right? So let's try to see what the main problem here is, right? To rearrange, what essentially we want is at the current position we want to put all the possible numbers. So when we are starting, right, at the first position we want to try 1, 2, 3 and 4, and then in the next position here we want to try 1, 2, 1, 3, 1, 4. Here we want to try 2, 1, 2, 3, 2, 4 and so on. And that is how we can generate a permutation. So yeah, that is our recursion function. Okay, so let's try to code that recursion function, and okay, whatever the hell that is. Okay, so let's try to code the recursion function, and I'm gonna call it calculate the what are we calculating? We're calculating the permutation, right? So at the current position, what we want is we want to store the possible numbers. So let's say we are permutating 1 to n. So we can iterate through all the possible numbers 1 to n. And now if it is not chosen already, right, if this number is not chosen, so let's actually add these things. So this will represent the permutation that we have. We have n, and then we have a array for chosen. Okay, so if it is not chosen, then we're going to choose it. So chosen I equals to true, and by choosing I mean add it to our permutation array, right? And then recurse again, and now let's unchoose it so that we can choose some other option at this position. And then permutation dot pop back, right? Now when do we stop this recursion? What is the base case? When we are done, when we have a permutation, right? So when permutation dot size is equals to n, now process your permutation here. So what, let's just print it like usual and return. Why is my intelligence so slow? Okay, so we should get permutations. So yeah, okay, we didn't get because we didn't call it. So yeah, we got all the permutations, and as you can see there are 24, that is 4 factorial. Now obviously you don't want to do this every time, you want to generate all the permutations. So C++ actually has a function. So let's say you want to permutate 1 to n, so you create it into a vector. Okay, now what we want to do is do a do while loop. Okay, now process your permutation here. So do processing of your permutation and then next permutation. So next permutation, what that does is it creates the next permutation in place in memory. So it updates a to be the next permutation. Okay, so let's say actually, so we want to permutate 1 2 3 4, right? So what's happening now is, first of all we print 1 2 3 4, then next permutation generates the next permutation, we print that, then it generates next, we print that, and when there is no more permutation to generate, it returns false. So if we run this, we get all the permutations. Now what next permutation actually does is, if you hover over it, okay, there's no docs. Okay, so what it does is, you can actually just see, right? So cpp reference next permutation, you can read about what it exactly does, but let me tell you, it calculates the next permutation in lexicographical order and updates a correspondingly. So what lexicographical order means that if you have two permutations 1 2 3 and another is 1 3 2, then notice that the first position where they differ, the second permutation is bigger, right? So that means this is lexicographically bigger. Okay, so that's how you compare. So it generates the next lexicographically bigger permutation, and it keeps on going until it ends up with something like 5 4 3 2 1, right, where it cannot get any bigger lexicographically. So what that means is, if your permutation is not sorted initially, you will get not all the permutations. So what you want to do, if you have an unsorted permutation, you want to sort it, and then you'll get all the permutations. So yeah, that's how you generate permutation. Now you might be thinking that we don't actually ever use this brute force of subsets and permutation, but you will be very wrong. I have actually used it many times in AdCoder problems especially, and many times in code forces as well. So if it is an easy problem, usually it's direct brute force, but if it's a bit difficult problem, what you have to do is, you have to identify some constraint on that problem by which you can reduce the, so you'll be given some bigger constraint, right? But you can identify something, get some observation, and reduce that constraint to something on which you can brute force. So this is a quite common uh, problem pattern, I guess. And I've actually noticed brute force problems mostly in AdCoder. So yeah, that was it. Now the next section is backtracking. It is a little bit more intelligent brute force, and it's not big of a deal. You can read it, but I'll cover it in the next video. So yeah, hope you like this video. If you did, leave a like, subscribe, and I'll see you never. I'm kidding. Next time.